Hello everyone, this is the challenge question walkthrough for Edexcel's Applied Year 2 textbook, and the first chapter is on statistics. Okay, so our first question is from exercise 1A then. And we've got this table here showing some data collected on the efficiency rating E of a new type of supercooled engine and operating at a certain temperature T. And it's thought that the relationship between E and T is of the form E equals A times T to the power B. And part A asks us to plot an appropriate scatter diagram to verify that the relationship is valid for the data given. So the first thing I want to do when I see this relationship here is to take logs of both sides to give us a linear relationship instead. And that will be easier to see on the scatter diagram, a linear relationship instead of an exponential one. So yeah, let's take logs of both sides. So log of E is equal to log of A times T to the power B. And then using log rules, we can split up that left-hand side into log of A plus log of T to the power of B. And then we can take the power of B down and multiply in front. So we've got log A plus B log of T. And here we now have a linear relationship, and that's going to be between log of E and log of T. B is our gradient, and then log of A is our y-intercept. Okay, and then if we do find the values of log of T and log of E for each of the data points we've got in this table here, the original table, then we can see that when we do plot them as a scatter diagram, they all kind of nicely fit, for the most part, on that straight line. And there's the line of best fit drawn in there. And part B asks us to find the equation of this straight line and to estimate the values of A and B. So from this diagram, we can see that roughly the y-intercept is about 1.1, and that's going to be equal to log of A. And then we've got the gradient, which we can work out using the rise over the run. So the rise, we can say, is, if we're looking at this triangle here, the rise is going to be about 1.1, and the run is about 0.55, I'd say. And the gradient is going to be negative, remember, because it's sloping downwards. So here, we've got the gradient, which is B. It's going to be equal to about negative 1.1 over 0.55, which is negative 2. Okay, and then the last thing we need to do is find the actual value of A rather than log A. So we can solve this equation for A by raising 10 to the power of each of the sides. So 10 to the power of 1.1 is equal to 10 to the power of log A, because log is log base 10. So we can then cancel these out. So we get A equals 10 to the power of 1.1, and if you use your calculator to find out that value, so 10 to the power of 1.1 gives you 12.58. So A equals 12.5892, which we can round to, let's say, 3 sig fig, so 12.6. Three significant figures. And then finally, for part C, give a reason why the model will not predict the efficiency of the engine when the temperature is 0 degrees. Well, we could say that this is the model here, log of V equals log of A plus B log of T. If we plug in T equals 0, then we're going to have to evaluate log of 0, which is undefined. If you imagine the graph of log of x, that looks something like that. So there is actually no value, or tends to negative infinity. So it's undefined at that point. And also another way you can think about it is if we plug in 0 to this value of t here, then we're going to get the efficiency is equal to 0, which doesn't really make sense. So there we go. And then finally, for exercise 1b, again, we've got another table with some data for two variables, x and y. We're asked to calculate the PMCC for suitably coded values of x and y and state with reasons whether the data is more closely modeled by a relationship of this form, y equals a b to the power of x, or by a relationship of the form y equals k x to the power of n. So again, to both of these, we can do a similar sort of thing as we did for the first question. So we can take the logs of both sides. So log of y is equal to, using the log rules again, we've got log of a plus log of b of x, or x log of b. And then on this right hand side, we've got log of y once again, is equal to log of k plus n log of x. Now, thinking really carefully about what are going to be our variables here, we've got log of y on both sides. The other variable on the left-hand side is going to be the x. That remains as x. Then on the right-hand side, we're going to have log of x instead. So we can see where these two different models are coming from now. One, we've got log of y against x, and the other one, we've got log of y against log of x. Okay. So here's our table with the values for x, y, log of x, and log of y. And what we can do now for this first one, this first model here, is to put the values of x and log of y together into a calculator to calculate the PMCC. And if we do that, that's going to give us r equals 0.985, okay, to 3 sig fig. Then if we do the same, but with log of y and log of x, I'll do that in purple here. So log of y and log of x. So take these two values here, calculate the PMCC, and that's going to give us 1.00 to 3 sig fig. So clearly, the most appropriate model is going to be this one. So y equals kx to the power of n is going to be more suitable, as the PMCC is closer to 1, or is 1 to 3 sig fig. So that suggests a closer linear fit for log of y and log of x. So y equals kx to the power of n is our answer. And that is the end of this challenge question walkthrough. I hope you enjoyed this and found it useful, and I'll see you next time.